Let's see what chapter 4 is about. Wave functions and quantum states. A wave, something vibrating, frequency, wavelength, spread out functions. I think that's a mathematical description of some wave. And quantum states we've already seen in the atom, especially of electrons. The orbits are quantized, but now it seems it's the combination of the two. So maybe the wave functions describe the various quantum states. Of the atom. Multi-electron atoms, matter waves and light quantization, electrodynamics. So what am I encountering here? Atoms, electrodynamics, mathematics, equation, electrons, height of a surface, water waves, Greek symbol, amplitude, complex amplitude squared. Ambient pressure, space curvature, strength of electromagnetic field. Object that was waving was not a physical medium, but the mathematical object was complex amplitude squared. Words, but what do the words mean to me? Atoms, matter wave, Schrödinger, waving, energy quantum levels. Let's move on. Schrödinger matter wave equation. And there is, what is that symbol again? A wave function. Schrödinger wave function. And they're doing all sort of things here with the wave function. There's derivative, and there's an operator, and there's another operator. Newtonian equation, total energy of the particle. Equations for electromagnetism and light. Electromagnetism and light. Schrödinger matter wave equation. Total energy, kinetic energy, potential energy, matter wave equation. Matter wave. Does that relate to the Broglie's matter wave? Wave equation derive the energy quantum levels of hydrogen Schrödinger successfully used his wave equation to derive the energy quantum levels. There it is. Wave equation to derive the energy quantum levels. So this wave equation describes the quantum levels of the electrons in the atom. And he talks about a matter wave, EI. Some wave like the pilot wave of de Broglie. And here they look at the compare it to the energy of a system. Kinetic energy and potential energy. And Coulomb electrostatic potential energy. The way to use Schrödinger equation first to define the potential energy function. The way to use Schrödinger equation is first to define the potential energy function for the system, and then solve the equation for the total wave function. The potential energy function. So, like you've got a planet and a satellite or something orbiting a planet, and it's got various potential energies with respect to that planet, depending on where it's orbiting. So it's something like that. So if you can define that, then you can, if you can define the potential energy, and they're talking about Coulomb forces, electrostatic forces, then maybe you can get the wave function. The total wave function actually consists of an infinite family of functions. One for each possible state of the particle. Quantum numbers. So defining that function is also problematic. The total wave function actually consists of a finite family of functions. So that wave function or wave equation, or maybe they're talking about the potential one. The total wave function consists of an infinite family of functions. So it's mathematics trying to get a function to describe the quantum states is quite a challenge. And the various quantum states probability that the electron is located somewhere in space and time, quantum state, probability. Now they're talking about probability of locating an electron in space and time. And here they're talking about complex complex mathematics, complex conjugate. Schrödinger. Atmospheric electricity. And they mention electron orbits, eigenvalue quantization. Detailed mathematical technique which is simple to apply to all quantum systems, involving his new idea of the wave function to describe quantum states. And here they're talking about wave, amplitude, crest, wavelength, complex numbers, complex algebra. The mathematics of complex algebra has to be used to describe this wave function. So it's mathematics and complex algebra. Complex conjugates. And here they're doing mathematics with the complex conjugate. The product is comes to that, which is a real number related to probability. So Schrödinger's wave function was related to the probability. So it's probability between 0 and 1. Schrödinger mathematics was the square root of the probability of finding an electron at a particular place and time inside the atom. Aha. The amplitude of the wave function defined in Schrödinger's mathematics was the square root of the probability of finding an electron at a particular place and time inside the atom. In fact, what was actually intended by the wave function was technically far more complicated. So you can find the probability, but what was actually intended by the wave function was technically far more complicated. What was up with this wave function? The wave function represents the specification for the electron in one quantum state within the atom. Represented the specification for an electron in one quantum state within the atom, which was indexed by the quantum number for its energy. Angular momentum along the axis. Through a function which is a function of position and time. Angular momentum describe the state of the electron, spherical coordinates, Legendre polynomials. What is this? Computed elementary electron probability clouds. Probability clouds. So these are probability clouds. The quantum numbers. So these, if I can just see, there are three quantum numbers. L, M, and N, I think. And they talk about angular momentum. We saw something that the angular momentum is quantized. That linear formula or directly proportional formula. And now they've got probability clouds. If it's got where the electron will be positioned in space and time. Depending on its quantum number, the probability clouds produced by this quantum function, I think, looks different. So it seems the function gives you the probability of what's the probability of finding these shells are brighter in certain places. Higher probability of finding it there if it's in that quantum state. And the projection of its angular momentum along the axis, applying a magnetic field to the atom. Ooh. So, probability of finding the electron at certain positions. Quantum state, Neumann, quantum mechanics, Heisenberg's Uncertainty Principle. Schrödinger's quantum theory involve wave functions, physical objects, electron in quantum state, matrix of values, the many observable outcomes of observation, matrices, commutation. Now I've got matrix algebra. Calculating the spectral line frequency, Heisenberg's matrix quantum condition, matrix mathematics. Something about matrices, matrix mathematics, electron in a quantum state, a set of probability waves, quantum condition, calculating the spectral line frequencies for hydrogen. Tedious and rather cryptic, we're willing to follow his laborious discussions. But within the matrix mathematics were hidden some crucial insights about how quantum systems are measured. So the mathematics contains some information about the measurements of the quantum states. Scattering of light by atoms. Developed this matrix approach to calculating how atoms interact with light. Matrix mathematics. The interaction of light with atoms. Scattering. How atoms scatter light. Electron is doing between measurements. What an electron is doing between measurements. Watching a person travel from one post to another. You cannot see what the person is doing in the dark. This is interesting. The analogy devised by him was to be sitting in the park in the night watching a person travel from one lamp post to another. You cannot see what the person is doing in the dark, only how they suddenly appeared at a lamp post. For the electron, this most literally means that Heisenberg interpretation that electrons do not really exist between measurements. And Heisenberg's matrix lists all of the possible outcomes of observations or measurements of what the electron is doing when it arrives at the lamppost. If if you were to measure, that is what you're going to find. But what is happening in between, we don't know. Now I talk about a wave function, measurement possibilities suddenly collapse into one state specific Copenhagen interpretation of wave function collapse. A measurement of an electron is like watching a man walking between lampposts. So these quantum states are quite complex. Or what it's doing in between the measurements, we have no idea. It's just, if you make a measurement, this is what you're going to find, what you might likely find. PhD, many world interpretations. Ooh, what the wave function of a system, quantum measurement. Where am I time-wise? 10 minutes. Heisenberg's second insight's a bit more to motivate. Splitting. The process of splitting allows the wave function across all the spawned universes. Ooh, multi-universe consideration, many world interpretation. Is it splitting up between many worlds and then collapse when you make a measurement? You find it at a specific place. It takes all possible paths. The universe splits into multiple copies depending on whether a single photon is measured to spin up and a spin down after 3 successive measurements. Many multiple copies. It seems there are various possibilities depending on what is happening. If it takes, this could be happening or this could be happening, and if you measure one of these states, realize Fourier analysis, complementary pair, electrical signal localized to a specific time. Electrical impulse is confined to a small time interval in a time domain. Time domain, frequency domain, frequency and time. What is going on here? Frequency and time. What? Fourier complex wave train momentum description. Reciprocal behavior between momentum and position, and also between energy and time. Momentum, position, energy and time. Heisenberg's Uncertainty Principle. Momentum and position, energy and time. There's the uncertainties. 2 equations. Momentum and position, energy and time. Atomic scale. You cannot know the speed of the particle, momentum, there's uncertainties. The uncertainties in energy. So here there is only mentioning the momentum uncertainty and the position uncertainty. Schrödinger's elegant use of mathematics, Heisenberg's uncertainty relations, accurate description of atomic structure and predictions for measurement outcomes. Several problems. Schrödinger quantum theory was not yet consistent with the special relativity. How the wave function for a quantum system collapse. Where are we on time? I think it started a new video. I didn't interpret it correctly, I think. So I went over 20 minutes. I think so. That's seconds and that's minutes. Edwin Schrödinger developed a mathematics for describing wave-like properties of electrons within atoms, probability of finding a particle in a specific quantum state. Mathematics, wave-like properties, probability of finding a particle in a quantum state. That's Schrödinger's wave equation. Heisenberg ignored knowledge about where the particle was before the moment of its interaction with other quantum systems. What? Upon making an observation of the state of a particle, the full wave function of all possible states collapses into only one. Upon making an observation of the state of a particle, the full wave function of all possible states collapses into only one final state, which is called the Copenhagen Interpretation. So the full wave function, the wave function describes all possible states. And when you make a measurement or observation, you get only in a certain quantum state. Heisenberg's uncertainty principle sets a fundamental limit to how well two quantities such as energy and time, momentum and location can simultaneously be known. What is its momentum? What is its position? What energy does it have at what time? The energy changes with time. And there's uncertainties in these values. Schrödinger and Heisenberg's quantum theory led to the first precise and mathematical consistent explanations for the structure of atoms. So together, first precise mathematical consistent explanation for the structure of atoms. So what is these two? Heisenberg talks about the momentum and the position and the energy and time, and Schrödinger is finding it at certain positions, the probability of finding it at certain position at a certain time, depending on the quantum states. So that's trying to get to grips with chapter 4, wave functions and quantum states.